Hello, my name is Jim Olson, and this is a video on my handout titled, "The Pythagorean Theorem is Your Friend." This is the handout, and we're going to be doing an example today. The Pythagorean Theorem tells us that if we have a right triangle, then the sum of the squares of the legs is equal to the square of the hypotenuse. A squared plus b squared equals c squared. If you're not familiar with the Pythagorean theorem, you might want to Google for it for a more complete explanation. Conversely, if we have three sides of a triangle in the relationship a squared plus b squared equals c squared, then we can conclude that the triangle is a right triangle. Since right angles are congruent and right angles are common and right triangles are common, the Pythagorean theorem can be used often. It's a very powerful tool. The technique that we're going to be showing here is that we can define a variable, which is an unknown, write an equation, and then solve the equation to find the value of the unknown. Now, if there's more than one variable, you may need more than one equation. So let's take a look at our example. It's called the folded corner problem. We start with a square piece of paper, and you might think of it as origami paper that's colored differently on the two sides. And we take this upper left-hand corner here, and we fold it over to this midpoint. This segment is equal to this. This is a midpoint. And this is going to form two triangles, region A and region B. And we're supposed to find the ratio of these two areas. You might pause the video at this point and see if you can solve the problem on your own. Here's one way to solve it. We're going to let the original square be 2 by 2 for simplicity. That way, when we take the midpoint over here, this is a distance of 1 and a distance of 1. So I'm going to define a variable, and I decided to let my variable be this distance right here on this particular right triangle. Since this total distance was 2, this distance is 2 minus x. At any point, please pause the video so that you can write down my steps. This segment right here is what we had before the fold, and this is the same segment after we had the fold. So this is also 2 minus x. I am setting up a second variable here, y, at least for the time being. So let's see what we want to do next. We're going to take a look at triangle A. And we're going to apply the Pythagorean theorem to triangle A. See if you can write down the Pythagorean theorem for triangle A and solve for x. Here is the Pythagorean theorem for triangle A. Leg squared plus leg squared equals hypotenuse squared. Here I've taken 2 minus x times 2 minus x. This is kind of nice because the x squared on both sides of the equation, if I subtract x squared, those go away. I get 4x equals 3 and x equals 3/4. That's nice that it came out that nicely. Now think about what you might want to do next. Now let's look at the two triangles. They're certainly not congruent. Triangle B is larger than triangle A, but they are both right triangles. And this angle are complementary. The three angles here add to 180, but we have 90 here, so these add to 90. These angles add to 90 in triangle A, so therefore, this angle is congruent to this angle, and this angle is congruent to this angle, which means we have similar triangles. Triangle A is similar to triangle B. So now I can set up a proportion. See if you can set up the proportion. X over 1 equals 1 over y. That's kind of the short leg over the long leg equals the short leg over the long leg. If I cross multiply, I get this. And X, we already know, is 3/4. The reciprocal of 3/4 is 4/3. So this turns out to be 4/3 down here. Pause the video and see what you think you might do next. See if you can finish it. Now we're ready to calculate the area of region A. 1/2 base times height for region A is 3/8. Now see if you can pause the video and calculate the area of region B. The area of region B is 2/3. And now we can find the ratio. The ratio of area A over area B is 3/8 over 2/3, which is 3/8 divided by 2/3, which is 3/8 times 3/2, and we get 9/16. Okay, that's a nice answer. But the question is, why 9/16? Is there some way of seeing it without just a bunch of algebra? Pause the video now and see if you can think of a nice way to show why this is 9/16. I'm sure there are lots of ways of seeing why it's 9/16, but here is a neat way to do it. I'm going to take this triangle here, which is 1 by 3/4, and I'm going to divide this side in 3, this side in 3, and this side in 3. I'm going to trisect each of the sides, and I think I'm going to just do it here, kind of crudely with a ruler here. This side is 4.5. 4.5 divided by 3 is 1.5. 1.5. And I'm going to do that on all sides, the hypotenuse here, and so on. So I've divided this side in 3 equal segments, and this side and this side. And now I'm going to connect here. This should give me parallel lines. And look at here, 1, 2, 3, 4, 5. 1, 2, 3, and 1. There are, in fact, 9 congruent triangles there. We're going to be doing something similar. That was a joke. Something similar down here. See if you can pause the video and see how we want to divide up this triangle. Yes, we want to divide each side of this into 4 parts. So I'm going to measure here. Looks like about 6 centimeters. 6 centimeters divided by 4 is 1.5. 1.5, 1.5, 1.5. And I'm going to do this on all 3 sides. This triangle was 1 by 4/3. And so I'm dividing this into 4 parts. So let me go ahead and make the parallel lines here. And sure enough, we have 1, 2, 3, 4, 5, 6, 7, and 5, and 3, and 1. So there are 16 here. There's 9 up here, and there's 16 down here. All these little triangles are congruent to one another. In fact, you could even get the distances if you want to check that they're congruent. This shows why the ratio is 9/16. It's often nice after you do a bunch of solving of equations and you get an answer to figure out why it's really true. I hope you've enjoyed this video on using the Pythagorean theorem as a problem-solving tool. Have a great day.